Detachment by raindrop impact may be followed by 5 transport mechanisms. These are raindrop-induced saltation, raindrop-induced rolling, transport in suspension, flow-driven saltation, flow-driven rolling. When raindrop-induced saltation occurs, particles are lifted up into the flow by the impacting raindrop. The particles that are lifted into the flow travel downstream as they fall back to the surface. The transport rate varies directly with the distance those particles travel during fall. This is equipment which enables us to control the conditions of flow over a soil surface in terms of flow depth and velocity. Using this equipment, it has been shown that raindrop-induced saltation discharges sediment in a linear relationship with rainfall intensity and flow velocity when flow depth is held constant. The distance the particles travel depends on flow velocity and the height particles are lifted into the water layer. In some cases, the height of the water surface constrains the height to which the particles are lifted. In deeper flows, dissipation of drop energy in the water layer restricts the height to which the particles can be lifted. As a result, we have an interaction between flow depth and drop size, which is represented by this function shown in yellow in this equation. That function is shown graphically in this graph, and the peak for any given drop size is related to the maximum height which the particles are lifted. As noted earlier, the transport rate varies directly with x, and x actually varies with particle size and density in addition to the height at which particles are lifted. Particles such as carbon are less dense than sand and consequently are transported at a faster rate than the mineral particles. In this equation, Ks is influenced by the mass of material lifted into the flow by drop impacts and the characteristics of the material being transported. Ks is influenced by how particle size and density affect x. When raindrop-induced rolling occurs, each raindrop impact causes the particles to roll a certain distance, where they stop and wait till the next impact. With raindrop-induced saltation and rolling, material travels limited distances from the point of drop impact. Only impacts close to the downstream boundary actually cause discharge. Fine material remains suspended in the flow and moves without further influence by raindrop impact, while the large particles sit and wait for the next drop impact to move. No matter where the impacts occur, fine material moving by complete suspension will be discharged across the downstream boundary. In this experiment we have water flowing over a mixture of biochar and sand on the left hand side and at the top on the right hand side. When the rain starts, there's a flush of fine material moving in complete suspension. That's followed by biochar moving by rolling and saltation. The large particles of biochar are angular and so they don't roll really easily. The sand is moving by saltation throughout the experiment. So in this case we have fine material moving suspended in the flow, and we have coarse material moving by saltation. That is for sand as well as the biochar, and we also see biochar moving by rolling. It is well known that flow-driven erosion can occur if the flow has a shear stress which exceeds a critical value, which depends on the resistance of the soil surface to detachment. However, at lower shear stresses, flow-driven saltation and rolling can occur if the shear stress exceeds the critical values for that to happen. When flow-driven saltation and rolling occurs, the loose coarse particles that have been detached by raindrop impact move without further stimulation by raindrop impacts. Flow-driven saltation and rolling are much more efficient transport processes than raindrop-induced saltation and rolling, because the particles move without having to wait for raindrops to stimulate that to happen.